Okay. It's a little cluttered up here now, but you have a point on a curve, and you've got an origin somewhere, maybe here. So you've got this R of t vector that's tracing out the curve, and we're familiar with that idea. And the R of t can be given as a vector, x of ti plus y of tj plus z of tk. The end of the R of t vector at any time is at the point x of t, y of t, z of t. So we have a point on the circle, and I've depicted the point by this. Okay, and you have an R vector out to this point. I didn't want to draw it to this point because it's going to clutter up the picture. We don't even know where the origin is. The origin might be over here, and your R vector might be this. It doesn't matter. Wherever you put your origin, your v of t vector here being the derivative of this doesn't care about constants, and the position of the origin is basically constant. And you don't need to understand that really, but if you do, great. Okay, so at some time t, you got this point on the curve. You got the velocity vector v of t obtained by taking the derivative of the r of t vector. And you have your acceleration vector that you get by taking the second derivative of your r of t vector, or the derivative of your v of t vector. The acceleration vector, and we've already developed this, we've already seen this, so the acceleration vector has components parallel to your velocity. In this case, that would be this component. Now it's parallel, but in the opposite direction, the way I've drawn the acceleration vector here. If the acceleration vector was out here, then the parallel component would be in the direction of the velocity vector. You've also got your unit tangent and unit normal vectors, which we looked at last time. So once you know your parallel component of the acceleration, you subtract it from your acceleration vector to get the perpendicular component. Okay, just turn this vector around, add it to this, you get this. And this is a parallelogram here. It's actually a rectangle. So again, this is something we've already seen and we've already done. I'm just reminding you so you have a perspective. So these are all things that are easy to calculate. And the bottom line then is that the v of t vector, it's the first thing you calculate probably. You can get its magnitude, just square root of the sum of squares of its components. And that would be like x prime of t squared plus y prime of t squared plus z prime of t squared, square root of that sum. You have your perpendicular component of the acceleration vector. You've got to do a little work to get it, but it's not that bad. So now you know speed and centripetal acceleration, because the perpendicular component of your acceleration vector is, again, the component that changes your direction. Parallel component is the component that speeds you up or slows you down along that curve. But this is your centripetal acceleration, and you feel that. You feel like you're being thrown toward the outside of the curve. That means you've got to be exerting a force to stay on the curve. And we've, again, talked about that. Okay. So I'm going to make a sweeping statement. For the instant, the motion is the same as if it's on a circle of radius v squared over a perpendicular. Okay, your speed over your centripetal acceleration. And we call that rho. We don't want to call it r because we're using r. When I originally wrote it down, I wrote r. You just have to munch it out and fix that. Okay, not only that, but it's centered along this line from here parallel to the a perpendicular vector. Why is it centered along that line? Because the, centripetal acceleration, centripetal means, well, back toward, okay, back toward the center of the circle. And we established that over here. Okay, so there's the radius, and the center is along this line, the a perpendicular, or I'm using capital N for the unit normal vector, okay? And of course we know from what we've done before that your unit tangent vector is v over the magnitude of v, and your unit normal vector is a perpendicular divided by its magnitude. And it can also be, the unit normal vector can also be obtained by taking the derivative of the unit tangent vector and then dividing by the magnitude of the unit tangent vector. No, I didn't exactly say that right. Taking the derivative of the unit tangent vector and dividing by the magnitude of that derivative. Okay, had to think back to what my words were. Okay, anyhow, there's your normal vector. Easier to get this way than the other way. The other way is a computational mess for most curves. Okay, so there it is, and we call that our osculating circle. If I had all the letters in there, it would be better. I'd love to see osculating circle. You can see I have the gem in there because I left it out. Now, osculating means kissing. Okay, so the circle kisses the curve right here. It goes along with the curve for a short distance at least. Now, let's clarify. Well, let's leave it at that for right now, and then in our next clip, we'll see where we go from there.